Okay, this is Learn a Log Submission 2. And once again, this is Marzaria Conway. This is the front of my notebook. And we start off on 14.1, which is tessellations. And we learn about what tessellations are and how to make them. Polygons that don't fill the plane, that don't overlap. And they don't have any gaps. And we also found out how to measure the planes and figure out how to measure the angles evenly with the formula that was given. And I thought it would be more than tessellations, which is why I had some blank pages. The next was simple closed surfaces. And we learned the definition of what a simple closed surface was, as well as polyhedra and polyhedrons. I've learned that spheres and solids are not polyhedras, but square pyramids and triangular prisms are. They're polygons that are three-dimensional. And a simple closed surface has one interior, no holes, and it's hollow. We learned about, prisms, right prisms, pyramid parts. We learned what a truncated polyhedron was, as well as cylinders and cones. Cylinders are circular, and cones, they're a little bit, they have one base. And we did some work on some in the notebook to learn the different types: tetrahedrons, cubes, octahedrons, dodecahedrons, isohedron. I think I said that right. And we learned how to figure out the vertices. We learned how to figure out how many edges there were. We learned a formula to where you add the vertices and the faces, and it gives you the number of edges. They have to equal. So the vertices plus the faces of each one, like for instance, a cube has 6 vertices, and 8 faces. And you add them up, it gets 14. And you add the edges plus 2, it should give you the same number. Thus the formula F plus V equals 2 plus E. So the number of faces and the vertices plus each other equals 2 plus the number of edges. That's how you figure out if it is a regular polyhedron. The next week we did triangle inequality, and we learned about the sides. The base of the theory is the sum of any two sides must be greater than the length of the third side. So for instance, if you have 7, 5, and 12, it could work because each time you add, it's going to be greater. It should be 7, 5, 7, 6, and 12. But every time you add, it's going to be greater than the side that it is. They can't equal each other. So for instance, if you have 5, 5, and 10, it won't work because 5 plus 5 equals 10. Two of the sides have to be greater than the other one. We learned with equilateral triangle is 60 degrees all the way around. Isosceles, the bases are congruent, and the scalene triangle, the largest angle is opposite of the largest side, and the shortest side is opposite of the smallest circle. Then we did some work in the book to give us some examples and learn on. We was given different legs with the possum noodles because we don't have the little tools, and just try to work them out and see exactly what size you can use as well, and what would it make a triangle or not. And here at the bottom we have the results of those as well, what will work and what wouldn't work if you try to make a triangle out of them. Basically the theory is you can't have a side that's less than the two sides added together. It won't make a triangle. And then after that, we learn lesson 12.1, triangle congruent properties. And this is where we learn about the same size, same angle, it has the same shape. They do not prove that they are congruent if it's angle, 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 and angle, side, side, or side, angle, angle. The four that works are side, side, side. Here's an example of that. Side, angle, side, angle, side, angle, and angle, angle, side. Those are the properties that work. I also learned about the two proof column. It's a method that basically shows how to prove that these triangles are congruent, because basically you have to make sure the triangles are congruent with each other. And you have your statements and your reasons. The statements is going to be to the left, and the reasons are going to be to the right. And then some of them are going to be given, like for instance, you see that on this one, angle D is congruent to angle A. Angle A is congruent to angle D, and it is given because you can see that they have the same lines represented. The angles are the same measure, as well as B and E, and that you see that A and B is equal to E and D. And so since that is there, you see that this is the angle side angle property. And with this one, pretty much everything is the same, and you see that this is angle angle side theory. And we have to do some of our own as well. Give it some examples. I drew my little lines on this one because it was side, side, side. And corresponding parts of congruent triangles are congruent, as you see that they are all congruent with each other. This one was a definition of side, angle, side, showing that when the vertices, triangles meet at the same vertex, that these form angles, basically right here. And this is how you know that these two are angles, because sometimes the points and the lines are going to intersect, as well as down here showing that these two sides are to each other. Next, we had similar triangle and other similar figures, showing that the same shape, same angles, but they might not be the same size. And basically this lesson was trying to show, formulas or things you can use to show that they are similar, whether it's similar triangles or similar polygons, that though they might not be the same size, you want to prove that they are basically have similarities between each other. And when you do the equations, the common ratio of the lengths is the scale factors. And also we learned about the side similarity for triangles. And if the lengths of the corresponding sides of the triangles are proportional, then the triangles are similar. And then you also have the side angle side similarity for triangles. If two triangles, two sides, one of the triangles are proportional to their corresponding sides, and the other triangle and the included angles are congruent, then the triangles are similar. And you also have the angle similarity for triangles as well. Down here we worked on trying to figure out how they were similar with the equation. And you have the small triangles over the large triangles. So you, for instance, you had the 4 and 6, which is, where's my 4? Right here, over here, these were the two sides, and you was trying to find X over here. So you put the 6, which was the small triangle, for the big, and then the big one is what we're looking for. And you do the math, and you got X equals 9. Those how you figure it out. Here we have a few more examples working on trying to figure out these angles. That's what's missing. Then the same thing, you're looking for X, you plug in the equation and you get it. And that's pretty much it for these lessons. I did update my glossary. It looks a lot better now, with all of the definitions up to this point. This is my A, B, and C. This my D, E and F, G, H, and I, J, K, L, M, N, and O. And I'm thinking I'm probably going to have to write some of these on the back of each page because P, R, S, and T have a lot of definitions. So more than likely, I'll put them on the back going forward. There's S, and there's T, and G. You know everything for Y and Z. So that is the notebook for this week.